This one is going to get a little bit more abstract. So we're still trying to calculate work, right? The work required to move some physical object. So here we have a cable, which is 200 pounds heavy. This cable is 100 feet long, and right now it is dangling off the top of a skyscraper. And we don't want it there. We want to reel it back up. So once again, we would like to calculate the amount of work this will take. So remember, we will be taking force against distance traveled. Well, we don't have a formula for this force function, right? What force is working on a cable? Well, gravity would be working on this cable. But even though the force is going to be the same everywhere, right? We can say that gravity works on such a huge scale, we can just pretend that it is a constant locally. Then I still need to be careful because some parts of that cable have further to go than the other parts of that cable. See what I mean? Here I've drawn, or somebody's drawn, a picture. Here's our building. Here is our cable here. And notice that this little piece of the cable right here, which has been labeled as delta X, it's got to go halfway up that building. But parts of the cable at the very top don't have to go that far. As soon as I pull them up over the edge, that's it. I don't need to put any more work to get that part of the cable up. As I reel this in, parts of the cable down at the bottom, they have the farthest to go. I have to put the most amount of work in to pull those up over the top of my building. Does that make sense? The more I reel in, the parts of the cable that I've got, once they're on top of the building, I don't put any more work into them. I do just the minimum amount of work that is expected of me. See, professors do that too. Shh. Well, that means that each different part of this cable, if I chopped it into pieces, I would be carrying it different distances. Pieces of cable at the bottom have farther to go than pieces of cable at the top. That means I will need to apply more or less work to them. All right. Now, this is a bit of a funny picture. I have not said this yet, but you've probably noticed already that this picture puts 0 up at the top of the building. Sure, fine, why not? And it puts 100 down here. So even though this is the x-axis, it has been drawn vertically, right? So I have sort of turned my picture over like this, and now I can see that, oh, that's just the x-axis. We just rotated it. So the idea is we're going to say with a piece of cable at exactly x coordinate xi, how much work is required to reel just that piece of the cable up to the top at x equals 0. So we're going to use the actual weight of this cable because that weight is calculated in pounds, and pounds are in fact the unit of force for the American system. So if the whole cable weighs 200 pounds and the cable is 100 feet long, then each foot of the cable weighs 2 pounds. I'll say that this cable is, the weight of this cable is 2 pounds per feet. So that's sort of a density, if you like. This is telling me, how do I convert from a number of pounds of this cable to a number of feet of this cable to a number of pounds of force that's being acted on that length of cable by gravity. So I can use that to say that the weight of a cable that is delta X number of feet long, well, that's going to be 2 delta X pounds. That's the amount of force I'm being exerted on there. Now, I need to multiply by the distance to get my amount of work. How far does this segment have to be pulled up the building? It has to go a distance of X. Yeah? So coordinate X here is telling me I've got to go X number of feet up, right? Here at the very bottom, X coordinate 100. This piece of cable has 100 feet to go before it makes it all the way up to the top. X coordinate 10. This piece of the cable only has to go up 10 feet, and then we've reeled it in. So each individual piece of the cable has this amount of work required to bring it up to the top, 2 times xi star times delta x, and I can add those all up to get my approximation of the amount of work. My approximation does better the more sub-intervals that I have. So in the limit, I get my integral, and my work integral here is just going to be integral from 0 to 100 of 2x dx. Excuse me. Altogether, we can do our fundamental theorem of calculus, and the answer will be we need 10,000 feet-pounds of work in order to reel that cable in.